In this video we're going to have a look at the photoelectric effect and the dot points from the syllabus that are relevant are the ones that are highlighted there. So we'll look at explaining it in terms of the photon, defining some of the key terms, and then after going through this video you should be able to solve some problems involving the photoelectric effect. Now it makes sense to follow on from black body radiation with the photoelectric effect because the application of the solution that Max Planck derived is what Einstein used to help explain the photoelectric effect. But we first of all need to talk about what the photoelectric effect is. It was a phenomenon that was documented in the late 1800s and observed by a few different scientists doing different experiments. But the main observation that was recorded was that electrons were able to be displaced from the surface of a metal if there was light shining on that metal. So the idea here is that light could cause electrons to be emitted or ejected from the surface of a metal. Now, one of the more prominent people involved in making these observations was Hertz. And he kind of observed it by accident. He was actually conducting an experiment to detect electromagnetic waves, and part of his apparatus involved the production of a spark every time an electromagnetic wave was detected. And in order to see that spark more clearly, he conducted the experiment in a dark box, and he noticed the spark was much smaller. So he conducted a few further experiments and a few more observations and discovered that it was actually ultraviolet light, or the lack of ultraviolet light, that had an effect on the spark itself. So if we look at a simple diagram here, so we're going to deal with this as being light and this being an electron. So that's sort of a simple way to visualize what's happening. So light incident on a metal surface, and then the electron being ejected from that metal surface. So there are a few specific observations that are important here, and the observations are relevant because we need to be able to identify how the wave model either is or isn't going to apply, and then how that allowed the particle model of light to be further developed. So the first thing that was of note is that only light of a certain frequency or above a certain frequency, so only light with a high enough frequency could cause electrons to be emitted. And that leads to a particular frequency that we need to be aware of, and that's known as the threshold frequency. So above the threshold frequency, and the symbol that we use for threshold frequency is F with a subscript 0, so F naught, electrons were immediately ejected. And note the word immediately here. It's an important one to pay attention to. And we'll come back to why that is when we look at the actual observations. And if you had any light below F naught, no electrons were ever emitted. So when the frequency of light is above the threshold frequency, electrons were immediately emitted. And when the frequency was below that threshold frequency, no electrons were emitted. So there's the first observation of this phenomenon that's important. The second one is that increasing the light intensity had an effect on the electrons that were being ejected, but not the effect that was expected. So increasing that intensity of light increased the number of electrons, but not the maximum kinetic energy with which they were emitted. So when we're talking about their maximum kinetic energy, we're talking about the fastest that the electrons are being ejected from the surface. But we'll come back to energy because it's a little bit more of an encompassing concept rather than just dealing with speed of the electrons themselves. So the reason why those observations are important ones to note is that the wave model couldn't explain them. And we'll have a look at why that is. And we'll link into some of those points that I highlighted earlier. So the first one, if we're dealing with light as a wave, given enough time, electrons should always be emitted. So, and the threshold frequency shouldn't be valid either, given that light of any frequency should be able to transfer enough energy to eject electrons. So two aspects here that are important. The first is that the time aspect. So we should be able to see electrons being ejected if we allow enough time to pass. So that means that the energy from the light is going to build up in the substance, and then eventually the electrons gain enough energy that they can then escape. That means that we would expect to see a delay, but the observations of this phenomenon, there is no delay. The electrons were immediately emitted, as I mentioned earlier. The second aspect then is the light of any frequency. So the idea of a threshold frequency isn't relevant if we're dealing with light as a wave, because any frequency should be able to provide enough energy given enough time that the electrons should then be able to be ejected. So there's the first flaw with the wave model to explain this phenomena. The second one is the issue of intensity. So greater intensity of light, or of a wave, means greater energy. So if we're dealing with light as a wave, that should mean more intense light should result in more kinetic energy of the electrons that are ejected, not that there are more of them. So there's two reasons why the wave model of light didn't work in explaining this particular phenomenon. In order to explain the observations, it came down to Einstein in 1905 when he applied Planck's solution to blackbody radiation to the photoelectric effect. And in doing so, he significantly advanced our understanding of the nature of light. And in 1921, he was actually awarded the Nobel Prize for his work in 1905 on the photoelectric effect. Now, Einstein didn't actually conduct the experiment. He was able to just explain how the observations matched with Planck's theory, so applying that idea of energy being contained in packets. So some of the things that are important to note here, first of all, is this idea that we have photons that have energy. And we've already seen the equation that's relevant there, but I'll just jot it down again here. So the energy of the photon is equal to hf, so f being the frequency of the light, h being Planck's constant, and E being the energy of the photon. The next thing that is important in Einstein's explanation is that there is a minimum energy required to cause the electron to be emitted. And so to remove an electron from a solid, so that wording there is sort of the definition of this idea, and that definition is one that you can find in the glossary, and it's the definition for work function. So work function is the amount of energy needed to remove an electron from the surface of a metal. an equation that's relevant here that's not actually in the data booklet. It's just a rewording of that first equation that we've got above. The work function W is equal to hf naught. So you can see the W is an energy, f naught is the frequency, and so we still have that same sort of structure to that equation. We're just looking at a specific frequency relating to a specific amount of energy. So that value of f naught, as we mentioned earlier, is the threshold frequency, and again a definition for that that's from the glossary, and that is that it is the minimum frequency of a photon that can displace an electron. There's two definitions that are important in explaining the photoelectric effect. And the next important observation then relates those two types of energies together. So I'm just going to use a bit of shorthand notation here and identify that if the energy of the photon is less than the work function of the solid, then no electrons are emitted. So that matches up with the observation. When the photon energy is less than the work function of the substance, no electrons. If the photon energy is greater than the work function of the substance, the excess energy is transferred to the electron, and it's transferred as kinetic energy. Now there's another equation here that is important, and it's one of the equations that's in the data booklet. So if we look at that relationship, we're looking at the kinetic energy. The maximum kinetic energy in particular is then going to be equal to the difference in those two energies, so the energy of the photon and the work function of the substance itself. Given that we know what the energy of the photon is, we can then write that as Ek is equal to Hf minus W. So that's the equation that's in the data booklet. So looking at the maximum kinetic energy of the photons compared to the work function of the substance, you can take that a step further and substitute in what the work function is, so that's Hf minus Hf naught, but it's that highlighted equation that's the one that's in the data booklet. And just to notate what each of those variables are, so Ek is specifically the maximum kinetic energy. So not necessarily going to be the case that all of the energy of every photon is going to be transferred to the electrons that are ejected, but some will gain that maximum kinetic energy, and so we're only really looking at the maximum when we deal with this equation. And given that we have energy involved, that's going to be measured in joules. Note again, because the amounts that we're dealing with here will be so small, sometimes the values might be stated as electron volts, but generally speaking, it's going to be in joules. So H is Planck's constant, as we've already seen. F is the frequency of the photon. In hertz. And W is the work function. And again, that's going to be measured in joules. So there's the equation that's important for the photoelectric effect. We also need to have a look at what it looks like graphically. So I'm just going to sketch a graph here to represent this phenomenon. So on the vertical axis, we're going to have the maximum kinetic energy of the electrons, so Ek. On the horizontal axis, we're going to have frequency F. Now, if we're looking at a particular substance, we know straight away that there is some threshold frequency that's important, so that value F naught. We know that when the energy of the photon is less than the work function, then there's going to be no electrons emitted, and that means that there will be no kinetic energy of the electrons. So what we would see is that up to that point, the energy of the electrons that are being emitted is zero because there are no electrons being emitted. After that, we have the equation HF minus W. So as the frequency increases, that means the energy of the incoming photons increases, and the excess energy is transferred to the electron as kinetic energy. That means we're going to see a linear trend line where we have an increase, and the gradient of that trend line is going to be h. Now, if we were to track that line back and project it back to the vertical axis, the value that we would see there would be negative w. That's because this trend line is given by the equation E is equal to hf minus w. So you can see there the gradient is h, f is the horizontal variable, E is the vertical variable, and w being the vertical intercept. Now, if we had a different metal, that means that the threshold frequency would be different. So that means that the graph looks a little bit different in that the zero energy will extend to a greater frequency, but we still have the same gradient for that trend line. So the gradient there is still going to be h. The difference comes down to the work function in that last term. So you can see on that second line that I've just drawn, the intercept on the vertical axis would be lower. But ultimately, for the photoelectric effect, the gradient will always be constant. It's that value h. The horizontal intercept will vary depending on the threshold frequency, and that correspondingly has an effect on the vertical intercept if you were to extend that trend line down to that vertical axis, where that corresponds to the work function. Now, the last two things to note here, sort of consequences then of Einstein's application of Planck's theory. We know that, as we've already seen through the observations, in these scenarios energy is transferred immediately. So there's no delay with energy having to build up. Either there is enough energy or there isn't. So that means that the wave model definitely doesn't apply. And finally, the greater intensity of light doesn't mean that we have more energy in a wave. What it means is that we have more photons. And because each photon has the same amount of energy, that means that we have more total energy, but each photon still has the same energy. So when we have a greater intensity, that means that the maximum kinetic energy of the ejected electrons won't increase. It just means that there will be more electrons because more photons are bombarding the surface. So there's a summary of the photoelectric effect. In class we'll actually conduct the photoelectric effect experiment and we'll attempt to calculate the value of Planck's constant and see how reliable the experiment is in terms of comparing it to the accepted value.